Now to take a closer look at water. Where is it in a transformer? First, it is necessary to discriminate between two measurements used for water. One is water content. Content refers to the relationship between the water mass to insulation mass. The typical range for water content in the cellulose insulation of a transformer is between 0.5% under new conditions and about 5% under aged and wet conditions. Another relevant measure is called water saturation. Relative humidity or water saturation has the same meaning, but when referring to gas, we refer to relative humidity, and for solids or liquids, the correct term is relative saturation. Relative humidity is often used in terms of meteorology, for example, while talking about the air in a room, which would typically be 40%. This measure can also be applied to transformers. A typical range can be expected to be between 0.5% for a new transformer up to 30%, or sometimes even 50% for an extremely wet, aged transformer. Water saturation or relative humidity relates the actual water mass to the maximum water mass a material can take up. This process can be explained in more detail. Consider that there is oil, and one tries to mix water with this oil. As soon as some drops of water appear in the oil, the relative humidity exceeds 100%. So, relative humidity and water saturation tell us about the maximum capacity, the maximum water uptake capacity. Another very common example is the air. What would be expected if air has 100% relative humidity? 100% relative humidity actually creates fog. As long as the water vapor is dissolved as a gas, a nice clear day will be the result. But if the water forms droplets, fog is created. The effect is similar with oil. So, to reiterate, water saturation is humidity relative to maximum water absorption capacity. To convert one measure to the other, the so-called moisture isotherms can be used. In the graph shown here, on the left-hand side can be seen moisture content, and on the bottom, relative saturation. By observing the temperature, the user can go from one measure to the other. For example, 10% relative saturation at 20 degrees Celsius means 3.5% moisture content. So, one measure can be calculated from the other and vice versa. This illustrates how moisture is taken up by oil and by cellulose. Mineral oil consists of saturated hydrocarbons, which can only dissolve very small quantities of water. Water is therefore measured in parts per million, or ppm, representing very small quantities of the order of micrograms, for example. Aged oils have polar impurities, such as acids. These acids are able to bond more water, and therefore water solubility will be low for new oil, but it will increase with aging of the oil. In contrast to oil, the cellulose is very different in its molecular structure since it consists of glucose rings with polar groups. These OH groups are very active in attracting water. Therefore, cellulose or paper can take up a lot of water. The water receptivity of cellulose materials is typically 2,000 times higher than that of oil. There's a process running in a transformer which is called moisture diffusion or moisture thermodynamic equilibrium. Every system tends to reach equilibrium. Moisture equilibrium is driven by differences in water potential. This approach is very theoretical, but it can be broken down to a very practical approach. The relative saturation of adjacent materials becomes equal under equilibrium conditions, providing that the same temperature and pressure exists. For equilibrium, the relative humidity of the air will be identical to the moisture saturation of paper and of oil. For example, a sheet of paper will try to reach equilibrium with the air surrounding it. So, if there is a 40% relative saturation in the air, what will there be in the paper? After a while, the paper will have 40% as well. Equilibrium processes need time. This will be emphasized later. The same happens in a transformer. Under equilibrium conditions, there is the same relative saturation in oil as in cellulose. If a transformer is considered to be under equilibrium, there will be the same relative saturation in oil as in cellulose, for example, 3%. The air outside of a transformer has, for example, 50%, and it tries to add moisture to the transformer in order to reach equilibrium. This is prevented by using drying systems. The dehydrating breather has, say, 1% relative humidity, and so it will dry the air in order to prevent it from moistening the transformer. However, the transformer will become wet with time because of leaky seals, installation and repair, and also as a result of cellulose aging by oxidation and pyrolysis. So, water is a self-perpetuating entity. If there is water in the transformer, the water concentration will increase faster and faster because of the aging process, which is accelerated by water, and which will produce even more water. It is a self-accelerating or autocatalytic process. Some examples of contamination levels. A new transformer will have a relative saturation of below 2%, which means water content in the solid insulation is less than 1%. Under wet conditions, there is a relative saturation of more than 8%, maybe 15%, even 30%. Thus, the moisture content in cellulose will be 2.3% or more. The moisture content of the oil given in ppm, however, largely depends on temperature and aging. It is therefore not useful to apply limits based on ppm values. Rather, more important are the water content and the relative saturation of cellulose, which enable a judgment of the level of moisture concentration of a transformer. This graph displays the moisture content against age of more than 80 transformers located in European countries. Typically, new transformers have less than 1% moisture content. With increasing age, the water content increases as well, but you can see that there is also a lot of scattering. Thus, a transformer of 30 years of age can have a moisture content of less than around 1%, and a younger transformer can have a higher moisture content. So, it's not a simple relationship between moisture content and age. It depends particularly on the operation mode of a transformer. For example, how is it breathing? Is it leaking? And so on. Now some information about the time constants of moisture equilibrium. As mentioned before, moisture migration and equilibrium need time. This table displays the time for water vapor to migrate through a pressboard disc having a thickness of 1 millimeter. An oil-free pressboard has a time constant of moisture migration of around 1.7 hours at 20 degrees Celsius. This migration constant decreases to some minutes at 70 degrees Celsius. It is therefore highly temperature dependent. If the pressboard is impregnated with oil, the migration at 20 degrees Celsius will take 14 days. At 70 degrees Celsius, it is much faster. The equilibrium process takes only about 6 hours. Thus, at moderate load changes, the tester can expect more or less equilibrium. If a transformer is switched off and it is cold, equilibrium cannot be expected. Let's consider moisture distribution of a transformer. Where is the water and how is it distributed? Temperature is usually distributed such that the bottom of a winding is colder than the top. Because of this temperature distribution, there exists a reciprocal moisture distribution. Typically, the winding is wet on the bottom and rather dry on the top. The dielectric response method provided by Dirana will measure an integral moisture content. This means an average result. The degree of polymerization, or the mechanical strength, is typically worse on top of a winding than at the bottom. On top, the temperatures are higher, and so aging is much faster compared to the bottom. The following example illustrates the moisture distribution between the liquid and solid insulation. A large power transformer of 150 MVA will have approximately 7 tons of cellulose and 70 tons of mineral oil. Assuming a moisture content of 3%, this means that this transformer has 210 kilograms of water in the solid insulation. The oil will contain only 1 kilogram of water, although there are 70 tons of oil inside. Because of its molecular structure, oil can take up only small quantities of moisture. So, if one wants to dry a transformer, it is obviously not appropriate to dry the oil, because drying the oil will remove only 1 kilogram. It is the cellulose that needs to be dried.